going to record this lecture to the cloud. So if you have anything you want to talk about, or if you don't want your voice to be heard, this will be recorded and posted on the portal. So please don't just send me a chat message. The recording is began now. So everybody can see my screen. You can see this?
Yep.
Good. So what we're dealing with now is work. And work is a product of force and distance. So there's two things involved here. The work is the force and the distance involved in the problem. So far, we've learned about force, we learned about distance, but now we're going to combine them to talk about work. One thing about work is that it's a scalar quantity. And remember, scalar means it only has a magnitude. So there's no direction. Work does not have a positive or negative that indicates direction. So the positive and negative for work does not indicate direction. What it means is work into system and work out of system. So input and output. So if you're putting work into a system, it's positive work. If you're taking work out of a system, it's negative work. So if we have an object on a surface and you're applying a force, right? Force applied, and it's going a certain distance, that's positive work. Friction is acting in the opposite direction. Friction will do negative work on the object because it's slowing it down, or it's taking energy, or we didn't talk about energy yet, but it's taking it out of the system. So positive work and negative work doesn't have to do with direction. So I can have that same situation and apply my force this way and have friction this way. This is positive work and this is negative work. But we usually do it, you know, like positive X, positive Y, just to keep it simple. The units for work are a joule, which is a Newton times a meter. And remember, a Newton is a kilogram meter per second squared times a meter. So a joule, and I gotta figure out how to use this eraser. A joule one joule is 1 kilogram times 1 meter squared over a second squared. That's what a joule is. Meters, that gives us our joules. So that's a little bit of background on work. Work is the force times the distance. You have to be moving for work to be done. So in this example here, right, this guy is holding up a briefcase, so he's applying an upward force, and he's not moving. So the work is equal to 0. Likewise here, the force and the distance are perpendicular. That also gives us a work equal to 0. The force, oops, an F, I'm trying to write an F. Not the eraser.
So when we get work, how would you like the unit to be?
The units for work should be in joules.
All right, so I should put J at the end of my answer?
Correct. J is always go at the end of your answer. Sometimes you'll
Okay.
see a Newton meter, like on a quiz or something, but that's the same thing as a joule.
Oh, okay. I'll remember that. Thank you.
Mm-hmm. So the force and the distance have to be in the same direction. So if we look at our guy up here mowing the grass, if I highlight what's going on here, his force is down the mower, right? There's his force down the mower. But the mower is moving in the positive X direction. That's the direction of motion. So only F cosine theta does the work. So that's where we get the cosine theta in the work formula. So work equals FD cosine theta in this case. He also has a Y component here. F sine theta, that does no work. No work is done by your Y component. So the steeper your angle, right? If your angle is steeper that you're applying a force, you have to apply a greater force to do the same amount of work because you're losing it to your Y component. So force and distance have to be in the same direction. And you can see that down here with our stairs, right? If you're going up at an angle, the distance times the force. And here our distance would be vertical and our force would be upward. Now this force here would be a net force, which we'll talk about later, but it has to overcome the gravity. So the distance and the force have to be in the same direction. So if we look at the lawnmower example, it says how much work is done on the lawnmower by the person in exerting a constant force of 75 newtons at an angle of 35 degrees below the horizontal and pushing the mower 25 meters on level ground. So the mower is going 25 meters, that's our distance. And the force that he's exerting is 75 newtons. So if we were to draw a free body diagram, right, we could do F cosine theta, this is F, this is the distance. Now, we're not worried about the weight here, mg, because we're moving it horizontally. We're only worried about the x component. So the work that we do is equal to F d cosine theta. Well, if F is 75, the distance is 25, then the angle is 35. We plug that in, put it into our calculator, if we can find our calculator. And we get 1536 or 1535.91 joules. That's the work done by our person here. I gotta get my other calculator. Oh, here it is. That's the work done in pushing this lawnmower.
So wait, do we ever?
What's that? Do you have a question?
I don't know. Yeah. Do you ever have to subtract by 90 degrees or no?
No. Well, if you're on an inclined plane, you will. We'll do one of those too.
Okay.
I have a question.
Sure.
So for work, do you have to let's say you're pushing a lawnmower, does the lawnmower have to be moving for you to be you could be pushing something, and let's say the lawnmower is not moving, let's say it's up against a wall, would that cause, I'm assuming there would be zero work in that, correct?
Yeah, that's the same as this situation here. So if this guy, right, where, I don't know, pushing on a wall, and the wall here isn't going anywhere, right? If it's a brick wall or something, right? If he's applying a force and the distance equals 0, that means the work equals 0.
Okay.
So that's a good question. Both those are good questions. Now we can see if we increase the angle to 65 degrees, if he's pushing at a steeper angle here, that the work is going to change. So if we go to a 65-degree angle at that same amount of force, now we only get 792 joules. So we're doing a lot less work for the same amount of force. So if we're going directly behind the mower at 75 newtons, now we're doing our maximum amount of work we could do in this situation for 75 newtons. So the taller you are, the harder it is to push the mower, the more work you have to do to push the mower, or the more force you have to apply to push the mower with the same amount of work. Here's another situation. Again, not very difficult. Why don't you guys try this at your seats and see how you do on this problem. Oops. Can't do the thumbs up thing here from screen share, so I'll just have to time it and kind of get a feel for how long it's taking. If I start talking and you're not quite done, or you need a little more time, just say something, say slow down. But this probably shouldn't be too big.
I think I got the answer.
You got the answer, Ken?
Yeah.
All right, so let's try this. Right, here we go with our free body diagram. We have a 50 Newton force at 30 degrees, and we're moving at 30 meters. So work equals FD cosine theta. Work equals 50 times 30 times the cosine of 30. $12.99 joules.
Yeah, so yeah, I put a decimal like 0.03 on the end of that. Should I not do that?
What was the 0.03 for? Oh, that's
Yeah, it's like,
oh, I got you. 1299.03.
Yeah, because it's like angle and cosine.
That's fine. It's not a big deal.
Oh, okay. Like I'll make sure not to just put
I mean,
the
like
whole
on
number
on the quizzes, it would be like 1300 joules is what it would say, right?
Oh,
Two
okay.
digits.
Yeah, gotcha. Gotcha, rounded.
All right. Now, here's one with an inclined plane. It says a 3 kilogram block slides down a frictionless inclined plane to 20 degrees to the horizontal. If the length of the plane surface is 1.5 meters, how much work is done and by what force? Now, by looking at your tests, I know you guys can do these inclined plane problems because you didn't get any of them wrong. So this should be fairly easy for you. So give this one a try.
All right, I got it.
You got the answer.
Yep.
Is it just you and me, Ken? Let's see who's here.
I don't know.
Responding in the
Oh, we
chat.
got
I'm
a
here.
bunch of people here.
I'm working.
Oh, there's some chat people here. I just can't see who's here.
No, I'm here.
I went to Zoom. Now I can check in on whoever's there. All right, so we have an inclined plane. We have an object on the inclined plane. The object's 33 kilograms, right? The weight of the object is down the plane. Only the x component, and this angle is 20. So mg cosine 70 is causing the work to be done. So the work equals mg cosine 70 times 1.5. That's our distance. Whatever that comes out to be.
15.
15?
I got 15 too.
15.083. So 15 joules. Good. Good job, class. Does anybody need any clarification on that? All right, let's try another one. Here we go. Here's a friction problem. A 5 kilogram block slides 10 distance on ice. If the coefficient of kinetic friction is 0.2, what's the work done by the friction force? Give this one a try. This one's a little harder. All right, so there's the free body diagram. To find Fk, we just do the sum of the forces into y equals 0, n equals mg, n equals 49 newtons, Fk equals 0.2 times 49, Fk equals 9.8 newtons. So work equals Fk d. Now we don't have a cosine theta here because it's 0. Cosine of 0 is 1. So work equals 9.8 times 10, 98 newtons. Now the numbers make that problem pretty easy, but that's how it's done.
Wait, isn't it negative because it's a friction force?
Very good, Ken. The work is negative because it's a friction force. And it's not going to be in newtons, is it?
It'd be joules.
It'd be joules. Good. Does anybody need anything else clarified there? All right, now the net work is the total work done on the system. So in the system, you have opposing forces. And the net work, right, the sum of the work is going to be equal to all of the works done, which is the sum of the forces, so how we've been talking about it. So the sum of the works equals the sum of the forces d cosine theta. And again, the units are joules. And here's just a simple problem to look at it. We have an applied force, a friction force, and a distance. So we would say the sum of the work is the sum of the forces in the x times d, and we have cosine theta, but we don't have to worry about it because it's 0. Cosine 0, which is 1. So the sum of the work, or the net work, is equal to 120 minus 5 times 0.8. So
Can you
the net
go
work,
back to the last slide? I wasn't able to write down everything from my notes.
all right.
Thank you.
Again, these slides are in the preview in the other PowerPoint as well. The one I gave out prior to class. That's where these slides are pulled from.
Fair enough. My bad.
That's okay. It's our first time with the PowerPoint feature. I was just reminding you for the future lessons. That's why I went fast, because I assume most people went through that PowerPoint before class.
All right, my notes are good.
So in this problem, when we're doing our net force here, we would just take that 115 times 0.8, and we get 92 joules. That's the net work done, is 92 joules. Now, if we look back on a problem like this problem, if we start this problem over again, oops. And I just add to it. If I just say a 3 kilogram block slides on a frictionless plane inclined 20 to the horizontal, if the length of it, how much work is done? Oh man, sorry, wrong way. Ah. 3 kilogram slides on a frictionless plane inclined 20 degree horizontal. If the length of the plane is 1.5, how much work is done if a force of, I don't know, oh my goodness, 15 newtons is applied up, oh my, that's annoying, up, sorry, every time I touch it, it moves, up the plane. So now when we set this up, right, same idea, 20, and we got our block, which is 3 kilograms. Now we have a 15 Newton force up the plane. We have the weight down the plane, and we want to know what the net force is. So in this case, we're looking for the net work. So we already learned, I don't want this W here, sorry. I got a little taken aback by the thing changing on me constantly. This is mg cosine 70. So we can see our two opposing forces here. So our net work is going to be 15 minus 3 times 9.8 cosine 70 times the distance, 1.5. Is it 15 joules? Or let's hope this doesn't turn out to be 0. .42 joules. So in this case, our net work is up the plane because we have a positive work from the 15 newtons and a negative work from mg cosine theta. Does that make sense? So gravity is always usually doing negative work unless something is falling, right? So gravity is down and then your force would be up, right? If it was a drag force, then your drag force would be doing negative work, slowing it down. So that's net work. These are all done, all these things are work by constant force. That means you apply the 120 newtons and the 5 newtons in this problem over the entire distance. Springs and elastic bands, they apply variable forces. So work done by a variable force, like if you're lifting with a workout band, you know the further along the workout you get, right? The higher the band or the more stretch in the band, the harder it is to use the band. It gets more difficult because variable forces like springs and bands change over time. They have something called a spring constant or an elastic constant. This is K. The units for K are in Newton meters, newtons per meter. And this spring constant is going to cause the force to increase, right? These are directly proportional. The force is proportional to X. As F goes up, X goes up, or vice versa. As X goes up, as the distance goes up, the force goes up. So this is known as Hooke's law. And the work associated with it is 1/2 kx squared minus x naught squared. So this again is your initial position, and this is your final position. So the work is going to change based on the position change. So if we look at one of these problems, to measure the spring constant of a certain spring, a student applies a 4 Newton force and the spring stretches by 5 centimeters. What's the spring constant? Well, in this problem, we have the distance, 5 centimeters. Now notice that's in centimeters. So that's 0.05 meters. So F equals Kx. Our force here is 4.0 newtons. And notice we use an X for distance. This is a generic term in this case. So to find K, K is going to equal F over X, 4 divided by 0.05, 80 newtons per meter. This is a Newton per meter. Work, or a joule, is a Newton times a meter. This is a Newton per meter. So those are two different things. This is not a joule. Any questions there? So this is a variable force, work done by a variable force. So there's a constant force, that's the FD cosine theta, and then there's a variable force. This one says a spring with a force constant of 50 newtons per meter is to be stretched from 0 to 20 centimeters. The work required to stretch the spring from 10 to 20 centimeters is more than, the same as, or less than required to stretch it from 0 to 10. Compare the two work values to prove your answer to part A. So here we're seeing that the first length of stretch is a lot easier than the second length of stretch. So if we're going to look at this, right, we know K is the same, 50 newtons per meter. And we're looking for the work to stretch it. Now our work formula is 1/2 K x squared minus x naught squared. So if we're going from 10 centimeters to 20 centimeters, is 0.01 and 0.02, and 0 to 0. We're not doing that one. 0 to 0.1. These aren't even right. Sorry, I screwed that up. This is 0.1 meters, 0.2 meters, and 0.1 meters. So for the first one, we're going from 0 to 0.1 meters. So the work is 1/2 times 50 times 0.1 squared minus 0. So the work done here is 0.25 joules. And we're going from point 1 to point 2. Now the work is 1/2 times 50 times 0.2 squared minus 0.1 squared. You get 0.75 joules. So you can see the second half from point 1 to point 2 is 3 times greater than the first half. And the total work is 1 joule, the total work, to go from 0 to 20 centimeters. You just add them up. Do you have any questions on that? All right, you guys try this one. It's a little tricky. It incorporates what we learned last time, so you're going to need the formula F equals ma. You'll need the formula v squared equals v naught squared plus 2a x minus x naught, and F equals kx.
Yeah, it's gone now.
Oh, no, I turned it off.
Um,
Sorry, did you need it up there still?
yeah.
Oh, I'll put it back. Not that. Not that. I want to see YouTube. Not that. That. All right, so for this problem, right here we have a train, and it's 5 times 10 to the 5th kilograms. And there's some force that it has, and it hits a spring, and it's hitting that spring with an initial velocity of 0.5 meters per second. Its final velocity is 0, x naught is 0, and x is 0.4 meters. So remember, F equals kx. Our goal is to find k, so that's F over x. So we got to find the force. So the force is equal to ma over x. So to find a, v squared equals v naught squared plus 2a x minus x naught. V squared minus v naught squared over 2x minus x naught equals a. Now you can substitute that in over for a if you want, or you can solve it separately. I don't really care. So that gives me 0.5 squared over 2 times 0.4. And I took the negatives out because they cancel. And I got an answer that's probably not right. Oh yeah, I'm sorry. 0.5. I got 0.3125 for the acceleration. In our case, it's going to be positive. It's slowing down the other way, but it doesn't matter. So now I can plug this into my equation for k. And this better be a big number because we're stopping the train here. I got 3.91 times 10 to the 5th for k. Big number. Any questions there? All right, we're going to try one out of our book that's kind of hard. On page 260, I don't have any more blank pages here, so I'm going to have to transfer this over to Zoom quick, to the whiteboard. On page 260, number 8. 260, number 8. It says, suppose the ski patrol lowers a rescue sled and victim having a total mass of 90 kilograms down a 60-degree slope at a constant speed as shown in the picture. So the picture looks like this. We got a slope. We have tension in the cord. We have friction up the slope, Fk, and we have the x component of the weight. So that means we have mg sine of theta here, and our normal force here, and this angle is 60 degrees. And it says, suppose the ski patrol lowers the sled having a total of 90 kilograms, so that's 90 kilograms in there. Down a 60-degree slope. If mu k equals 0.10, how much work is done by friction if it's moved 30 meters? How much work is done by friction? That's part A. A is work done by friction. Part B is how much work is done by the rope. That's the tension force. And C is the work done by gravity. And then part D is what is the network. Ran out of room. Oh, what did I do there? So we got a lot going on in this problem. This is a good one because you can see all the individual problems. Now this theta right here, right, if we draw out our diagram for our weight, right, this angle is 30 degrees. So this is 90 times 9.8 cosine of 30, 90 times 9.8 sine of 30. And there's your free body diagram. You should be able to find all of these different things using your free body diagram. You got to find T. It says we're moving at a constant speed. So if we're moving at a constant speed, what does that tell us about the acceleration? The acceleration is equal to 0. So the first thing we want to do is find our missing forces to fill in our free body diagram. We've got to find Fk and T. So we go back to our big three equations. Sum of the forces in the x equals 0, max. So T plus Fk minus 90 times 9.8 times the cosine of 30 equals 0. Well, we don't know Fk, so we can find that, but T is going to equal 90 times 9.8 times the cosine of 30 minus Fk. Sum of the forces in the y equals 0. It's not moving up or down. N equals 90 times 9.8 times the sine of 30. And then Fk is mu k n. So Fk is 0.1 times n. And since I don't have room, I'm not going to write that all out there. So that's 44.1 newtons. That's Fk. So that makes T 719.73 newtons. So we found T and Fk. So the work done by T, or work done by Fk, is 44.1 times 30.
Question: how were you able to get 41 for FK?
Because this is 441 times 0.1, the mu coefficient.
Okay.
Did I do that right? Yeah. 441 times 0.1. So the work done by friction is 1323 joules. Now that's going to be negative because the person's moving down the slope. The work done by tension is 719.73 times 30. Negative 21592 joules. The work done by gravity is 90 times 9.8 times the cosine of 30 times 30. Two 2915 joules. And the net work is going to be work done by gravity plus the work done by tension plus the work done by kinetic friction. That's your net work. That's all the works added together. So that comes out to be 0. The net work done.
So I'm guessing how you got FK was you times T by the coefficient.
times n by the coefficient, right? It's F mu K times n. So
Yeah,
I put that in there. I just wrote n again because I ran out of room.
Oh, okay, gotcha.
Now, the reason the work done is 0, the net work, is because it's not accelerating. If it were accelerating or changing its velocities, then you would have work done. So when the net work equals 0, that means it's in equilibrium, not accelerating. Now, that's a kind of complex problem, but you guys should be able to do that at this point without much. I mean, you should be able to do it without my guidance, really, especially this part up at the top here.
This is gonna be a dumb question. How were you able to find FK in that top question? The T plus FK?
Up here, the sum of the forces in the x.
Yeah.
I just looked at my free body diagram and combined all the forces.
So I'm assuming that would. I still don't know how you got FK. Because I get that that the first half of it is just the cosine.
How I got 44.1?
Yeah.
Yeah, that's what you're asking, how I got 44.1?
Oh, so you have to take the sine first, and then that becomes.
Yeah, you find the normal force here. Then you plug that normal force in here. And you multiply it times the coefficient that was given, 0.1. And that gives you 44.1.
And then you take the 44.1 times
Put it up here to
90
get to
up there. Okay.
minus. But yeah, because they're forces that oppose each other.
Okay.
Does anyone else have questions on this?
I have one. For the work of any of them, except for gravity in this case, because we already used the sine or cosine formula in finding the x or y factors, we don't have to multiply by the cosine of the angle and for the work equation?
Correct. The cosine for the work equation is the component.
Okay.
So if we have this situation, right? It's actually F cosine theta times D, but we just rearrange it to make it more convenient.
Okay.
So if it's in this, if this is F, that means the cosine theta equals the cosine of 0, and that equals 1. So you don't have to worry about it then.
Okay.
Does that make sense?
Yep.
So all we did was distribute, or I think that's the mathematical property, to move the cosine out to the end. So it just makes it a little neater. But this is essentially here, this is your F cosine theta. Now, if you have a box, I'll put it on the screen. If you have a box like this, and you're pushing on it with a force like so, at angle theta, now it's moving up the plane, right? So in this case, it's F d cosine theta. See how that works? Because F and D, you're only going to use the x component of D here, d cosine theta, because they have to be the same, in the same directions, that force and the distance.
Okay.
Does that make sense?
I think so.
So yeah, that's all that's happening there. All right, so now we get to try our new quiz feature. Send me a private message in the chat with your answer to this problem. This is worth 2 points, and I'll put it on your quiz grade.
And we still have to do that homework by Wednesday, right?
Yes. I
Gotcha.
think it's Thursday, isn't it? No, it's Monday, Wednesday, Friday, so it's
No, it says
whatever day.
Wednesday on it.
Is it the 14th? I got the 14th written down on my calendar, so I went with the 14th. Is that?
I
That's
mean, it says
Wednesday.
Wednesday, so yeah, Wednesday
Yeah.
is the 14th.
Wednesday the 14th. Oh, I wanted to pause this recording before I did the quiz. That's an error. Oh well.